And she will tell us what she does here.
She did the presentation.
Okay.
My thing.
Okay, so hi, thanks for coming. So I'm going to present you the work I did here as a postdoc since September last year. So I worked in Anne's team closely with Aga and in collaboration with Tony. And also with Andy on the CRM side and Audrey and Yao on the GCM side. And so I'm going to talk to you about how improving the representation of clouds in general circulation models, simulations, through analysis of cloud reserving model results and field data. And so in fact I chose this title because it was the title of the position I applied for to come here. And so as you will see, long is the road to improve the representation of clouds in GCM. So first, I'll tell you a few words about the methodology. So as you know, general circulation models, they resolve the atmospheric circulation at global scale during several hundreds of years, so that the horizontal resolution is still of the order of a few hundreds of kilometers. And so at this scale, also processes like turbulence, convection, and clouds are subgrid scales. And so we need to represent the impact of those processes on the large-scale circulation using an ensemble of equations we call a parameterization. And those parameterizations are running in each vertical column of GCM, so that it is possible to run the GCM in a single column mode by applying some large-scale forcings and to just focus on the parameterization behavior on an observed case. And in parallel, we have what we call cloud resolving models that are used to analyze cloud and understand cloud processes. And in those models, the resolution is of the order of 1 kilometer, so that most of the cloud circulation are explicitly resolved. And nowadays, it is possible to run such simulation over domains that are equivalent to a GCM grid size, like, for example, here, 200 kilometers by 200 kilometers. And so here the idea is to run in parallel SCM simulations and CRM simulations with the exact same large-scale forcings on observed cases, and then use those cloud resolving model simulations to test and improve the parameterizations of clouds used in GCM. So, as an illustration, I'm going to first say a few words about my past work I did on boundary layer clouds. And so here in GCM, boundary layer turbulence and clouds are mostly generally represented by considering diffusion on turbulent diffusion on the one side and representation of clouds on the other side. However, observation campaigns, as showed, as in this paper from Lemon and Pennell in 1976, that cumulus clouds are in fact the saturated part of some thermals that initiate at the surface and transport air from the surface right to the top of the boundary layer where they condense and give cumulus clouds. And so during my PhD, I worked on a parameterization of those boundary layer thermals by adding to the classical diffusing approach what we call a mass flux approach. And so in a mass flux approach, each atmospheric column is divided into two parts. So an ascending part with a mass flux F and compensated by slower subsidence within the environment. And so here we have the representation of a mean thermal that transports air from the surface to the top of the boundary layer, exchanging air with the environment, and then condensating and forming cumulus clouds. So that the vertical flux of quantity, like temperature or moisture, is a combination of a diffusive term, depending on the diffusion coefficient, and then a mass flux term, which depends on the mass flux within these thermals, but also on the thermal properties like temperature and humidity. And so here, when you develop a parameterization, your main concern is not only to get those flux of heat and moisture, for example, correct, but you also want to have them for the right reasons. And this means for some correct representation of the transport of mass and the properties of the structure that carry out this transport. And so here, I put some equations, not to scare you, but just to say that we solve some conserve equation to compute the properties of mean thermals, like mass, heat and moisture, and momentum conservation. And so we have some internal variables in the scheme, which are this mass flux, the mixing rates, entrainment and detrainment between the thermal and the environment. And then we also have a vertical velocity within the thermal, and temperature and humidity properties. And so here, the question is, how can we evaluate if the simulated thermal properties are correct? And in fact, it's really difficult to do that using observations because those quantities are very difficult to measure. And so this is why we use some high-resolution simulations, which are called large eddy simulation for the boundary layer, because the resolution is more like 50 meters to resolve the boundary layer circulation. And even with those simulations, it's not so easy to deduce the thermal properties from the simulation. Because in fact, it's not so easy to identify in the high-resolution simulation the thermals we are trying to parameterize. Why? Because the thermals, they don't have any properties that are constant from the surface to the top. I mean, here they are cloudy, here they are not. We know that they are mainly positively buoyant, but here, near the inversion layer, they are negatively buoyant. And if you just rely on the W threshold, this won't allow you to distinguish this non-local transport from the more local diffusive transport.
Well, what about other traces, like radon or?
So that's what we did. So I work here with Fleur Couvreux, which runs the MESO-NH high-resolution model in Météo France. And she did some simulation by emitting a passive tracer in the first layer of the model. And so this tracer is then transported within the thermals and cloud and everything. And so it is possible and then to identify the thermals by computing the probability density function of the tracer concentration at each level, and then choosing like all the grid points where this concentration is the highest. Well, like a way to track where the tracer has been transported. And then we add a threshold on W to have updrafts, the air going up. And so here you have an example of a vertical cross-section of the selected structure in a simulation. You see that we select the thermal from the surface to the top, and where here this area is the shaded area corresponds to the cloud. And so from this, it's then possible to deduce some properties of a mean thermal over the domain. And so to evaluate the thermal plug model I talked about before. And here it's just an example of what we did, some study about the entrainment rate, because it's possible to deduce this entrainment rate from the environment inside the thermals, from the large eddy simulation here using this sampling in black dots. And then we were able to test some different formulation of the entrainment rate in the simulation in the gray line. So, okay, this is an example of what can be done to try to improve the parameterizations of clouds using high-resolution simulation. So when I arrived here, however, I had to work with some high-resolution simulations performed with the framework of the Tropical Whirlpool International Cloud Experiment, WPIs, that took place in Darwin, Australia in January and February 2006. And so this is during the monsoon period there. And so you have an observational network that allows you to derive from large-scale forcing to run CRM simulation on a domain, over a domain of 200 kilometers side. And okay, so that's what there was an intercomparison of different CRM and did using Dharma, Sam, Mesoanate, with more bench of different CRMs. And here I show you the evolution of the precipitation over the 2 weeks period, where just to show you that we have here a first period with high precipitation corresponding to the active phase of the monsoon, and then a period with lower precipitation, which corresponds to the suppressed phase of the monsoon. And in this talk, I will mainly focus on this event here, event A, which is like the propagation of a tropical squall line over the domain. And I will also show some results from this event C, which is a stronger mesoscale convective system. And here, just to remind you that the resolution of the CRM is about 1 kilometer size. And so all those CRMs, they have still different dynamics and subgrid physics like the turbulence and the microphysics. Okay. So given that, I had to switch from those fair weather, non-precipitating cumulus clouds from tropical squall line. So which observational picture is a bit more complicated. So here it's from a study by Zipser in 1977, where he identifies the main components of squall lines from observation. And so he identifies the occurrence of successive convective updrafts that transport air from the subcloud layer up to the top of the atmosphere and progressively detrain into what we call the anvil region of the system, and in which we do observe some mesoscale ascent. And so you have condensation and ice formation in those updrafts, as well as precipitation. And here, below the anvil, they observe what they call a mesoscale downdraft that seems to be driven by the melting of snow here at the anvil base, and which transport air from the mid-troposphere with low equivalent potential temperature to lower level here. But they also identify what they call convective scale downdrafts, and which are more in the convective core of the updrafts, and associated with a heaviest precipitation, and which bring cool and saturated air to the surface. And so those convective scale downdrafts, they tend to stabilize the boundary layer by cooling it, so they tend to suppress deep convection. But on the other hand, they spread, they form like pools of cold air that spread at low levels, and at the edges of which new convection is triggered. So they also play a role in further deep convection trigger. And so here the question is, do we really need to include all this complexity in GCMs? So at least we need to include the processes that will be key for the heating and moistening profiles of the atmosphere, but also to derive the rain rates over the correct area, and also to have the correct flood impact on radiation. So in this talk, I'm going to focus more on here the vertical redistribution of heat and moisture by deep convection, by analyzing those vertical transport via updrafts and downdrafts in tropical squall. So, okay. So how do we represent those convective events in GCMs? So here I'm presenting you the parameterization used in GISS modeling, which is from Del Genio and Yao 1993. And so in which they use what I defined before, a mass flux approach. But this time, the vertical atmospheric column is divided into 3 parts. So we still have an ascending part into saturated updrafts, but we also have a descending part into downdrafts, and then again this compensating subsidence within the environment. So here, convective updrafts is initiated at flood base as soon as we detect an instability in the subcloud layer, and the updraft properties are then computed again by solving the conservation equations of mass, momentum, dry static energy, moisture, and by assuming some mixing rates and entrainment between the updraft and the environment, and also by computing here the mass flux at cloud base. And then at each level where an equal mixture of updraft air and environmental air is negatively buoyant, we initiate a downdraft, which goes down, and we compute its properties by solving the same conservation equation, except the one of the momentum. We don't have any W equation in the downdraft.
Can I ask a really stupid question? Why did downdrafts even form? Isn't it? I've never really understood.
That's a good question. I'm going to try to answer this in the next slides. It's not obvious.
Okay, good. I wasn't missing anything.
Okay, so, I mean, observations have identified that both updrafts and downdrafts are important for the vertical transport, so they have been introduced in parameterization by considering mean updrafts and mean downdrafts, but then, of course, yeah, you need to understand what drives those updrafts and downdrafts, why do they have their properties, and to try to represent that, and this is all the challenge here, because we don't know so many things about it.
What's the triggering criteria?
Sorry?
What triggers the updraft?
For the updraft, it's like an instability here in the subpad layer. Like it's warmer
So
due to the heat, sun heating, the surface heating by the sun.
and what's so it's not formulated in terms of convective available potential applications. What's the not that?
Okay. So where am I? Okay, so here I just want to mention that in the parameterization, what they call like those updrafts and downdrafts, they are mainly meant to represent what I call the convective scale, updraft and downdraft, in the observations, while all what's happening at the mesoscale somehow is not really explicitly represented in the model, but it's mostly like included here in these compensating supplements, which might also be a limitation of the approach. But so here this parameterization tends to represent the convective scale, updrafts and downdrafts, and so I would like to try to use the CRM simulations to evaluate if the computed properties of those updrafts and downdrafts are correct. And so the first step is then to partition the CRM simulation domain into those convective parts of the system and the stratiform part. Right. Okay. So this is done by Aga, who's using an algorithm that is meant to be able to compare directly the CRM results with the observations. And somehow you use the CRM output to derive reflectivity field that can be compared with radar reflectivity. And then by applying the same threshold on this reflectivity field, so here it's done at 3 and 6 kilometers, you can distinguish the convective region, somehow where the rain is heavy, from the stratiform region where the rain is lighter. And so here you have an example. So here is from the SAM model, an horizontal cross-section at a given time step, where here in black you can see the convective region of the domain, and in light gray the stratiform region, and then in white the remaining environment. And here there's a comparison of the convective area and stratiform area as given by the different CRMs of the intercomparison in different colors, and as obtained with the observation in black. And so what you can see here is that the CRMs are able to represent the correct convective area, at least for all the growing phase of the system. But then after a while, they tend to overestimate the convective area, and this might be due to the size of the domain and to the cyclic boundary conditions used in CRMs, because all what is leaving the domain here is re-entering it here. So this may explain why we have these differences here. and also why the stratiform area somehow is delayed in the CRM simulation compared to the observation. So we know we still have some limitation using those cloud resolving models, but still we can use them to try to understand those updrafts and downdraft dynamic.
And when you say cloud resolving, 1 kilometer is clearly cloud resolving sufficient for the size of these convective.
Yeah, of course it's.
Clusters.
Yeah, I mean it's not optimal. It would be better to have maybe 200 meters, but 1 kilometer is already okay to study. I mean, it's really to study the development and growing phase of the system. It's not the initiation or anything. So I think it's enough here to at least study those updrafts and downdraft circulation. But as we need big domain, we can't. We have to use it. Yeah.
What's the vertical resolution of these models?
I think it depends, but it's more stretched near the surface from 100 meters in the first levels to 1 kilometer up in the stratosphere. Here there are like 80 levels or something like that in total vertical resolution. So, okay. So we have done a first step by separating the convective region of the CRM from the stratiform region to try to be closer to the updrafts and downdrafts we are trying to parameterize. And here I would just show you, to mention, so here I've plotted the flux of moist static energy, so which is a combination of temperature and moisture properties of the atmosphere. And so for event A, so this is time over all the event and height. And this is the evolution of this flux over the total domain. And here I've partitioned it into the convective region, the stratiform region, and the environment. And I've done the same here with the flux of total water. And here, so it's just to show you that it seems that most of the flux of heat and moisture occur in the convective region of the cloud resolving simulation. So you still have some flux occurring in the other region, but it's less. And so this somehow means that in the GCM, when we consider that's what we consider, that most of those flux occur in the convective cores and not in the stratiform part. So it seems that at least at the first approximation, it's quite a correct hypothesis to do. And okay, so from now on, I will focus in this convective region.
So say that the subsidence region does not extend very far horizontally around the convective reactive region.
Mm-hmm.
Even with the net flux over the whole domain doesn't include this compensating subsidence. There's my area.
Well, it seems that it's very slow, and so it's still important, clearly, but it's not where most of the vertical transport occur. But this is compensating this vertical transport, so it's related and it's really important. Okay. So now we have identified our convective region. We still need to identify our updrafts and downdrafts that carry out the transport. So one traditional way to do it is to use what we call like cloudy updrafts. It's just to identify every grid cells where you have condensate, like liquid or ice, with a positive W threshold. Okay. And for the downdrafts, we commonly use precipitating downdrafts. This means all the grid points where you have precipitation, rain on droplet, and then a negative W threshold. So this is what is commonly done in CRMs. And here you have an illustration. So it's a 3D picture done by Aga from the sun simulation at a given time step. And where you can see here the cloudy updraft in red and the precipitating downdraft in blue in the convective region. And so one interesting point here, so you have here the equivalent potential temperature of the surface, and you can clearly see here low low temperature right behind, right here, so which is related to the formation of those cold pools I told you before, and so those pools of cold air, which are right under the precipitating downdrafts, and at the edges of which you have those convective updrafts. But so, okay, so doing this has some limitation, because you are not sure that, for example, all your cloudy points may contribute to the vertical transport. You may have some cloudy points that don't do any, just do some local mixing, but don't do any convective scale transport, and the same for downdrafts. And so it does not really allow to differentiate the convective scale transport from other more local transport. And so we wanted to try something else. And so here, for example, if you do this vertical cross-section of moist static energy, you can see here that it seems like the high moist static energy from the surface is carried up by convective updrafts, while the lower moist static energy at mid-levels is somehow transported down by convective downdrafts. And so this is something that has been highlighted in many observations. And so that's what we are going to use to try to identify our updrafts and downdrafts. So by computing at every level and time step the probability density distribution of the moist static energy, and then dividing all the domain into 4 categories of points. So the points with high moist static energy, comparison with the other points, points with like mid-high MSE, mid-low MSE, and then the point with low moist static energy over the domain. And so what we expect somehow is to find that convective updrafts are made of all the points that have high moist static energy at a given level, while the downdrafts may be constituted of the points that have low moist static energy at a given level. And so in addition to that, we'll use a threshold on W to distinguish upward from downward motion. And we are going to try different thresholds of the vertical velocity. So here are the results for the updrafts. So I made a categorization of 12 regions. So here you have the categorization with respect with the MSE value of your points, and then a categorization using the W with 0.1, 0.5, and 1 thresholds. And so here I've plotted, again, it's the same as before, sorry, the evolution in time and height of the MSE flux over the convective region. And so as you can clearly see here, and it's pretty nice, is that all this flux of moist static energy seems to be carried out by all the points that have a high moist static energy and also a vertical velocity higher than 1 meter per second. While all the other points over the domain does not seem to contribute to this MSE flux. And so these are the points we try to represent in our parameterization. So these are the updrafts we want to compare to. So now we have identified them. We can compute their mean properties. And so here I'm showing you some of them for, again, so it's an average over all the events for the Dharma model. And I've plotted the QV flux, turbulent flux, the area covered by the updrafts, the vertical velocity, then the QV perturbation with respect with the environment, the mass flux, and the buoyancy. And I've compared here results obtained with this traditional cloudy sampling in black with what we will call the high MSE sampling in green. And so, what you can see here is that the difference between the two sampling is not so different, it's not so big. We still capture the same amount of the vertical flux of QV, but we do include less points. So this means that here somehow we have excluded all those points that are cloudy but do not contribute to any transport. And so the point here is that we have the updraft properties. And so we can compare them to the properties simulated by the GISS model. So here that's what I did here in red. And who is laughing? So, and so you can see that you have a so you have an overestimation of the flux of UV here on this particular case. And this seems to be more related to an overestimation of the mass flux here, both in the low levels and the high levels. The QV perturbation is not is quite okay, and and we also have a strong overestimation of the vertical velocity within the updraft, which gives an overestimation of the area covered by the updraft. And so the different processes that might be related to this in the parameterization is the specification of the entrainment and detrainment rates between the updraft and the environment, and also the pressure perturbation. And so here, just as an illustration, I plotted also the mean entrainment and detrainment rates obtained in the CRM and in the GISS model. And so you can see that it seems that we overestimate this entrainment rate at the low levels, which may explain why the mass flux is too high. And then we clearly underestimate the detrainment at higher levels, which may explain why the mass flux is too high at low levels.
Okay, is the model we run is a single column model?
Yeah.
And CRM is a 3D model?
3D.
3D?
Yeah.
So it's CRM. Not CRM.
It's CRM, yeah.
But then how can you compare a single column model?
You're taking the average of the properties over the two-dimensional domain.
Yeah, but then still, it's the single column model constantly gets forced by the large scale forcing.
But we apply the exact same
you average
forcing.
the whole thing over the CRM, right?
Yeah, I mean,
Same forcing.
you apply the same
But
forcing
still,
at the boundaries.
the CRM is kind of allowed to develop its own circulation, its own dynamics. While you
Sub-grid scale.
Yeah, it's sub-grid scale in the yeah.
Okay,
So
well,
if you take okay, we talk.
I also don't understand how you can compare these things. Because, so in the CRM or SCM, so at every level is the percentage of updrafts and downdrafts, is that calculated or so? Or I think every level is just one layer, so it goes up or down.
Yeah, but okay. So here we have the schematic view of the CRM.
Mm-hmm.
So you have 1 kilometer grid size.
yeah,
So the clouds are explicitly reserved.
Mm-hmm.
Yes, okay. And so if you are able, let's say, to identify these clouds here in the simulation by selecting the grid that makes this cloud, and then do the same with the other clouds and all the different clouds, and you compute an average cloud from this.
Mm-hmm.
You can compute the properties of like an average cloud over this domain, right?
Yeah.
And then that's what you have in GCMs. The thing is that in GCM, so the grid is 300 kilometers. So all those processes, they are sub-grid scale.
Mm-hmm.
So that's right. You don't have any. You can't do that. It's just 1D. But so the point is, the point is to try to represent with equation the impact of this vertical
Yeah, I understand
transport.
that. But
Sub-grid scale.
you don't average the CRM over one height level, but you average only those grid boxes that you identify as updrafts.
Yeah, for this particular purpose. I mean, if I
But you
wanted to.
cannot do that for the SCM because you only have one layer.
No, the SCM has a subgrid scale parameterization
Yeah, that's all
of
the-
where it's going up, where it's going down,
Okay.
and where it's not
Okay.
doing anything. So you're trying to compare each of those sub-elements
Mhm.
to the sub-elements defined within the CRM more explicitly.
Okay, so the SCM predicts how many updrafts and downdrafts you have at the same
So
level.
SCM
It
is doing
calculates an area fraction.
So let's
Yeah,
say
yeah,
it's
yeah,
doing
yeah.
this. It's dividing your vertical column
Mhm.
into an ascending updraft, a descending updraft, and then
Oh, yeah.
subzets. And so
Yeah.
you compute the properties of this mean updraft and mean
Yeah.
downdraft.
Yeah.
That's what we do in the parameterization. And so then we compare that to the mean updrafts and downdraft properties we extract from the CRM simulation. But I mean, we could also just compare the mean profiles of temperature and moisture over the domain, over the total domain of the CRM, and compare that with the mean profiles obtained with the SCM.
Mhm.
This is the first step somehow. I didn't show that here, but here the point is to go deeper into this,
Yeah, yeah, I
to see
understand.
if we have those, if we are doing the subgrid scale processes correctly or not.
I kind of got this like. So, yeah, thanks.
So that graph that is for one particular GCM cell, where that is taking place, the updraft.
This is, I mean, it's a column.
It's, yeah,
I
it's
mean,
that
you have,
one column is
you have
being-
many different vertical levels, but you have one, it's 1D in the
So
column.
it's that column that's being compared, essentially.
Yeah.
Right.
The vertical profile over this column compared with the vertical profile average.
Did you use the GCM vertical resolution, or did you use a vertical resolution that was tied to the CRM?
Oh no, I use the GCM one.
Okay.
Yeah.
Okay. So there could, so part of it could be that you just with the resolution that we have is not sufficient to get the lower levels.
Yeah, I didn't do any test on sensitivity test on the resolution, but of course it can be rated. Yeah.
How do you plan to generalize these results and eventually tune the convective parameterization in the GISS model?
Okay, so I'm going back to the topic. So here I've shown that, okay, we have some differences between the GISS results and the CRM properties. And here I show you that it's because apparently we are overestimating the entrainment rate inside downdrafts, underestimating the detrainment rates. And what I wanted to show here is that we do seem to have a correct buoyancy profile. And in fact, the vertical velocity inside your updraft depends mostly on this buoyancy, but also on the impact of pressure perturbation on the W. And so, as we have a correct buoyancy profile, it let us think that we kind of underestimate the impact of the pressure perturbation on the W equation, And so, here, it's like I identified some points where we can work on the parameterization, like to try to have better entrainment and detrainment rates, and to include the impact of the pressure perturbation in the W equation. But okay, I'm not that far yet. So
I mean, those spikes there, they're single layers, right?
sorry?
The entrainment
Yeah.
value, there's nothing in the first layer, then there's something in the second layer, and then there's a little bit more. I mean, you've only got like 4 layers before it gets to
Yeah.
no entrainment, right? And then in
Here
the
it's like cloud based in the GISS model.
right, so that's like level 1, right? I mean, there's
yeah.
only one number
Yeah,
there, right?
yeah, yeah.
And then in the detrainment, that looks like it's level 1, 2, 3, 4. That's like level 5, and everything is detraining level 5, and there's no detrainment anywhere else,
Yeah.
right?
Yeah, I don't know which level it is, but yeah, apparently they are.
And this from the SCM, this is a line average over
Yeah, here it's the average over this
the
event.
entire year.
Yeah, so it's the entire.
But this is
It's like a
only,
day or something.
but this is only up to idiotropy speed, so what about
Yeah.
detrainment at
Yeah.
the higher level?
Yeah, I didn't mention that because yeah, in fact, as we are, it's not so easy either to define, to compute those entrainment and detrainment rates of the CRM, because you need to have some variables that are really conserved without mixing. if you have such variables, then you can follow its vertical evolution and deduce the mixing from it.
Right.
Because it just varies because of this mixing. And so here I'm using this moistatic energy, and in fact it's really conserved only below 6 kilometers. And above it's not really conserved. So that is why I just show results below, because I can't really, with those simulations, I can't really deduce entrainment above. Okay, so now I've done the same with the downdraft. And so first back to the CRM results with the 12 category of points based on their MSC value and W value. And so here, as you can see, the picture is much more complicated as for updrafts. So as we expected, we have most of the MSC flux here carried out by low MSC points in this region. But apparently, all different categories of W's contribute to it. It's not only the faster downdrafts, or the low values of W also contribute to it. But then it appears that we also have contribution to the MSC flux here in the high MSC points of in which region, and so which seems to contribute in the opposite direction, but as strongly as the low MSC downdraft. And okay, so from that I deduce the properties of what I call those low MSC downdrafts and the properties of the high MSC downdrafts. And first I show you, okay, on the same event, average with Dharma, the same properties. And I compare this time, so this low MSC downdraft with what people usually call precipitating downdrafts, in black. And so here you can see that it's clearly different. It's not like with the updrafts. Well, okay, so those low MSC downdrafts, they carry a positive flux of QB. And they are responsible for like 1/3 of the mass flux of precipitating downdrafts and covering 1/3 of the precipitating downdrafts. And they are clearly much more drier. And also here they are mostly negatively buoyant. Yeah. So it seems like it's a category of downdrafts which contribute positively to QB flux, have low QB, I'm not showing it, but also low rain, quite low W, and a negative buoyancy. And if now I add the mean properties of what I've called those high MSC downdrafts, then you can see that those downdrafts, they contribute negatively to the flux of QB here. So this explains why you have this somehow this positive flux near the surface and negative here when you look at all the precipitating downdraft. And so they are contributing to a mass flux and area quite equivalent of those low MSC downdrafts. And if you look at their buoyancy, they are close to neutral buoyancy, but slightly positively buoyant. And as you can see here, they are much moister than the mean precipitating downdraft.
So these are things that are going down even though that they're positively buoyant.
Yeah. Yeah, but in fact, to be honest, here I'm computing buoyancy without including water loading. So just using QB, we have different definition of buoyancy. So here it's the first definition using just QB. If you add the impact of the water loading, those downdrafts that might become negatively buoyant, but only at low levels, like below 3-4 kilometers. But above, they still appear to be positively buoyant. So
positively buoyant with respect to what?
To the mean environment.
The entire domain, or
yes.
just convective cluster?
No, the entire domain.
So they can be negatively buoyant with respect to some local area average, right?
Maybe. Yeah, but it's not really what we, maybe, but what we represent in those GCM, it's really like updraft versus downdraft versus mean environment. So it's just here all the way I'm analyzing the CRM, it's always to be consistent with what is done in the GCM. So you could do differently, of course. Okay, so those downdrafts, they contribute negatively. They have high QV, they have also high rain, W, and a positive buoyancy. And okay, here I'm showing the results obtained with the GISS model in red. Where again you can see that we overestimate the downward mass flux, and this is related to an overestimation of the mass flux, at least at low level, but also apparently an overestimation of the QV perturbation. And here the buoyancy is clearly much strongly negatively buoyant than in the CRM. And we don't have any vertical velocity equation, so, okay, sorry, this. Okay, the names are a bit messed up here. I don't know. This is the mass.
How do you calculate the turbulent flux in the single column? Is that the resolved one, meaning you just take the time difference, or that's the resolved plus the subgrid, or it's only the subgrid?
In the single column model,
Yeah.
it's like the area covered by the updraft multiplied by the velocity, and then multiplied by the difference between the QV in the updraft and the QV in the environment. It's not in time, it's more in space. Average. Okay. So the main, we still have trouble, so we overestimate the mass flux, but we do have a positive flux near the surface and a negative one above. So kind of a combination of those high and low MSC downdrafts. And so here is just one more slide, it's already late. To illustrate some parameterization issues, we can look at, so for example, how do we initiate a downdraft? So in the GISS model, we mix we consider a mixture of half updraft and half environment to be the properties of the downdrafts if it's negatively buoyant. And so here I plotted the MSC and QV profiles in the environment in black, low MSC in green, high MSC in blue, and high MSC updrafts here in purple. And so from this, what we can see is that those high MSC updrafts, seems to be there can be a combination of the environment and the updraft. And in fact, if you compute the fraction of environmental air inside the downdraft, you can find that it's like 60% of environment and 40% of updraft air. And so to initiate them in the model, we are using 50-50. So, okay. And so about the downward mass flux, we also consider in the model that at the initiation level, it's 1/3 of the updraft mass flux. And here, if I plot the ratio of downward and updraft mass flux, we find like between 20 and 40%. So again, it's not so far from what is used in the GCM model. But regarding those low MSC downdrafts, it's a bit more complicated. We don't really know why they're. In fact, the main point is we don't really know if they are really separate entities or if they are maybe just the end of those high MSC downdrafts that initiated by mixing between environment and updraft. And this is a concern. And to try to look at that, I've done started to do some visualization of the updrafts and downdrafts I'm selecting. So here you have the horizontal cross-section at different heights, 1, 2, and 4 kilometers, and of the 4 different categories of points for updrafts and downdrafts. So for updrafts, we mostly care about the brown high MSC updrafts here. What you can see from this picture is that they are not straight, but they are tilted. For example, here from the surface to 4 kilometers. And if you look at the downdrafts, you see that near the surface at 100 meters, we have both high MSC downdrafts and low MSC downdrafts. And this is quite consistent up to 1 kilometer. And then at higher level, we have mostly high MSC downdrafts, but they are more scattered than those large patch of low MSC downdrafts. And what you can see here too is that those high MSC downdrafts, they are right under the high MSC updrafts, while those low MSC downdrafts, they seem to be under the tilting updrafts at higher levels. Okay. And so I've just plotted here at the last slide vertical cross-section of so vertical cross-section. Here in black you have the updrafts, and in the four colors the different categories of downdrafts. And so you can see that those high MSC downdrafts, they are mostly like within the updrafts or right below them, which can be at all the different levels. And then we have those low MSC downdrafts here. And this still does not really tell us if we are really the same entity here from those levels to the surface, or these are two different entities that are driven by different mechanisms. And one last point here, again, a horizontal cross-section of the low MSC downdrafts in blue here, to which I have added in red the low MSC downdrafts from the stratiform region. And what you can see here is that, in fact, it seems that those low MSC downdrafts in the stratiform region are just a continuation of those low MSC downdrafts from the convective region. And in fact, those could be, in fact, be the cold pool I was mentioning before. So those pools of cold air spreading below the convective system. So, yeah, to conclude, I would say that I was supposed to improve the representation of cloud in the circulation model through the analysis of cloud weathering model and feed data. So, but there are many steps to go there, I think. And so the first one is to identify a key physical process of the cloud life cycle that seems to matter at global scale. And so this is the case of downdrafts, as demonstrated by many previous studies, as they strongly modify the boundary layer and they seem to play a role in further deep convection failure. Then you need to understand what the mechanism behind this process from observation or high resolution modeling. So here it seems that we have the impact of water loading, melting, evaporation, mixing, but we still don't understand everything that drives downdrafts at this point. Then we have to evaluate the existing parameterizations. So what I did with the GISS model, highlighting some weaknesses and strengths. And but then of course you have to go to the next step, which is to make some improvements in the parameterization or develop new ones. Then you need to run them in the whole GCM and study the impact on the global scale on some climatic patterns. And then, of course, we will identify new weaknesses, and you will need to go back there with other stuff and start all over again. And so I think that very long is the road to improve the representation of clouds. And okay, so I went as far about downdrafts here at GISS, but I'm as lucky as I can go on in Paris now with a permanent position in France. So I will be able to do that again and again for the rest of my life.
Can I ask my question again? So why does a downdraft form? If I've got buoyant air that's come up through an updraft that is warm, where you've had a little bit of latent heat release, and I mix it with environment air, surely that's still positively buoyant. Why does it go down?
Yeah. Apparently what we saw is that even if I'm not sure at this stage that the downdrafts are the same entity or different ones, it's that we seem to have different mechanisms that drive the downdrafts. One of them is evaporation of precipitation, for those which seems to drive the low MSC downdrafts. Okay. And then for the high MSC downdrafts, as I told you, it could be water loading, at least below 4 kilometers. I mean, it's because you have the precipitation falling.
Yeah. The condensate.
Precipitation, like rain
Right.
falling, and it brings your air down somehow.
Is that a frictional effect? No, they don't include that.
It's a buoyancy effect. Just that
So just because you've got a two-phase flow,
yeah,
and it's the bulk density of that that makes it negatively.
yeah. But then it's not clear what happens above 4 kilometers and where the downdrafts really initiates. And that's where it starts to be complicated, because there are some studies that argue that in fact this could be related to gravity waves too, somehow, because you have your convective system, it grows up, and then it reaches the tropopause, it induces gravity waves, and those gravity waves may induce some flow that comes back into the system, and which might start some air going down. And so if this is this, then it turns to be really complicated to represent. Maybe it can be done, but yeah, it would be very complicated to represent this effect on the downdraft initiation.
Well, isn't that just a statistical thing? You know, if you imagine you're going up, you're going to get some reflection back. You could set up a stochastic thing that says, okay, well, there's going to be this much of up and downing, and if some of those downings are going to cause.
I guess
mean,
it's possible to do it.
You wouldn't want to actually calculate what the gravity wave did. You just want to say, okay, well, there's variations, because it doesn't matter what the variation would come from, right? I mean, if you've got something that's an external force that's going to push something down, and then that's going to trigger a downdraft, then it doesn't matter what that push was. It could have been from anything. It could have been from a plane.
Yeah, but apparently it's what it looks like. That somehow, in many cases, it seems that there's something that forces the air coming down, and then you have this loading, and then you have this evaporation that just make it fall more. But yeah, how it started at first, it's not so clear, and even, I mean, you still need to represent that correctly. I mean, to know what it is and to represent it correctly if you really want to represent, to your parameterization to be able to represent different cases.
I mean, theoretically, though, I mean, if you say, okay, well, if it's related to gravity waves set up by the first convective plume, then the most amount of convection you're going to get, the more noise you're going to get in the large scale flow, and then you can just.
Okay, but then somehow it's a way of representing this physical process.
Well, you could just randomly move something down and decide whether it's negatively done.
Yeah.
How do you, in both simulations with the single column and the CRM, how do you trigger the convection? I mean, comparatively, I mean, how do you mimic the triggering of the convection in the CRM with the single column in order to be comparable?
It's just that you start with the same initial profiles. You run with the same large scale forcings. So I didn't run the CRM simulation, I'm just using it, so I'm not sure they are doing anything.
I know there's
to
no
start
triggering, I mean, it's just explicit.
I'm not sure, I think
Sorry.
it's just triggered by itself, and then in the GCM, it will compute the profile, and then the parameterization will trigger
it's explicit.
whatever time is going to trigger.
So your results are not going to depend also on the trigger and on your single column, or on what kind of.
Yeah, it depends on that too. Here I focus more on the mean over the whole event, just to see the mean properties. But the timing of triggering is quite okay, in fact, in the simulation. The timing of the convective event is okay. But
because I mean that's another discussion on convective.
But here I don't really focus on this transition or triggering question, more on the like life cycle after it has been triggered, when it propagates. But it's another interesting thing.
Are there differences between different CRM models, or are they representing pretty much the same thing?
No, I've not shown that here. But we have because I show mostly Dharma results, but we have the results from all those other CRMs, and they all have different ways of computing the dynamic, and also all the processes that are subgrid scale. So so in particular with the microphysics of ice and so on. And so this, I didn't show it, but this is going to, in fact, the CRM are giving some different results too. And in particular for the downdrafts, because for the downdrafts it seems as those microphysics process are really important. So yeah, it's a good point that it's not even obvious we can really trust the CRM for all those downdraft questions.
But it's clearly a more solid basis than just making something up as we go along.
But,
Yeah, no,
but
of
if you
course,
had an
but-
ensemble of CRMs, you might
You have to see some of the CRMs that wouldn't put they need to see some other HRO. Some of the CRMs are even poor than the GCMs.
so like it's better to do Monte Carlo then, right? It's better to do Monte Carlo simulation or whatever.
But what's your what distribution you're going to pull from? You can't just take the observed distribution of clouds and convection, can you? Because you need to know how it's going to change under climate change, right?
Yeah,
So you can't just do something empirical like that. It has to be based on some physical understanding.
The CRM results here very much to the all the CRMs are pretty much tuned so that they match the observation, because this is a test case. Everyone spends pretty much a year just tuning the CRM until it gets to all the points. So
But then you have to take it on an out of sample case, right? Isn't there something that they leave out of their tuning? Hopefully.
well, you tune it for this case, then you run it for the next
Right.
case, and it's one more difference.
Do we have any hope that they're going to converge? I mean, for instance, radiation models. Like if you look at line by line, they all converge. They all give the same answer for the same
in
result.
three inter-comparisons to this right now. In all three of them, when we first get all the results, they're widely different. All by the second or third submission, all of them pretty much converge to the same. And then the next inter-comparison.
Yeah, but somehow.
Well, that's the way it is.
Yeah.
You consider radiation and parameterization?
Well, no, but line by line radiative transfer models all give the same answer, give the same profile, right? So, that means that that's a solved problem, right? And we don't need to worry about it too much anymore. But and then we can tune the GCM radiation to any one of those line by line models, and if it gives the right answer, then we're good. But this, if we're going to tune the GCM to a CRM, which might not be representative of the real world, which is going to be very different to another CRM, then there are issues.
Yeah, for sure.
With the world.
Yeah.
And what's the computational bit? Do you know these CRMs? If you actually had them, if you implemented this in a GCM, this sort of CRM thing.
You mean
what's
super parameterization?
Yeah, sort of like that. Super parameterization, which was proposed like a decade back.
Well, I guess that if we have issues here, as we are discussing, the CRM are already issues. So if you put them in every GCM grid box, I guess you will still have the same issues.
No, I'm just
I
wondering
mean,
the
what
cost
the
of.
microphysics is doing and what the
Well,
low-level clouds with such resolution.
It just goes to the resolution. So, you've got one box versus 200 by 200, right? So, and then you've got to reduce the time step. So it goes up for every doubling of resolution. It goes up almost by a factor of 10.
You go with super parameterization, they're not using a fully three-dimensional
No,
CRM,
they can't-
they're
they can't
only
do
doing
it.
two-dimensional, so that's also the strength on the flow. And so there you go. There are all these issues. Do you orient your grid, east-west or north-south, or do you try to do some mixture?
That's obviously a stopgap. It's not obviously the thing we do. But what about something like, is there any, I'm talking to some people at the Machine Learning Institute, right? And they're very keen on having, computers work out what the most interesting thing about a high-resolution simulation is, and then trying to encapsulate that directly. So you come up with not a physical parameterization, but maybe a neural net parameterization of what's going on in the high resolution model to push directly into the GCM. Is
You
that
mean like
an interesting way to go?
more statistical approach?
Yeah, it's basically a statistical approach.
For me, it's not, because, I mean, okay, you can do statistics and maybe it's a good way of doing it, but then, I mean, what I like in this kind of approach, parameterization approach, is that you really try to understand what's going on. I mean, okay, we can tell if I have such condition, I'm going to have this by statistics, but then somehow if you don't try to understand why, what's going on, and try to, I mean, the exercise of trying to put into equations what's going on, for me it's really the most interesting part, because you just try to explain the reality with simple equations.
Isn't the neural network still empirical?
Oh, totally empirical. But you run it, but you do it using, a lot of test cases for the CRM that cover all potential things that might happen, and then you extract some information like that, and then you use that within the GCM.
Oh, but the problem that you were mentioning earlier about what's going to happen as well.
No, because the CRM is physically based, right? So you can put it through any parameter space that you want, right? So if you think that there are parts of the parameter space that we're not touching now, but will touch in the future, well, you can do a CRM case for that if you had confidence that the CRM was doing anything correct.
But in some ways you can think of this physically based approach as just a really low order neural network approach. You're essentially trying to fit a model, whatever physical picture you attach to it, you're trying to fit a model with just a few parameters. But you're trying to fit a model with
This is a very complex thing. I mean, you saw the pictures of where there were updrafts and where there were downdrafts. Right. Our brains are not very good at trying to work out exactly what's going on there. Whereas maybe a data mining approach might be able to see something that we don't see, maybe at first hand.
Okay, let me ask a stupid question. Now you do all these things about deep convection clouds, about real clouds. Then why didn't you start with real clouds?
What
And
do you
then
mean?
just regular shallow convection.
Yeah,
And the
that's what-
GCMs.
She started with shallow
I
convection.
started with that.
Then
That's what I did
why?
here.
With the shallow convection, it's very easy. You're not limited. You always have to reproduce this at zip structure. With the shallow convection, you don't need cold pool. You don't need this.
Yeah,
You
I know.
don't need. You
But
have
that's what I
very
did.
orderly.
I did a parameterization.
Yeah.
That it's now in the LMTs.
What about
LMT.
Model E?
Yeah,
This
okay, I
is
did
what
my
I was
PhD
curious
at
to see
LMT.
how.
So it's now in the LMD, new version of the LMDZ model, and we saw the first results show that indeed it greatly improved the low cloud cover in the trade wind regions over the globe. And so now they're analyzing those new simulations, but it seems that
What
we
means
made progress
great?
by doing this. What?
What means great? From 0 to
Yeah, from
10
0.
to the -5.
No, from no clouds at all in the trade wind region to a consistent 20% coverage or something like that, compared with the Calypso, the last Calypso observation I looked at. And, so people are working on that too.
Because for me, that seems to be more important than.
I don't
I might
know.
be wrong. But
No, this is clearly important. It has been shown and discussed a lot in the last years with the local feedbacks in the GCM. But for tropical convection, I mean, the mesoscale convective systems are really important too. Yeah. It's important.
I think that's a good end statement. So let's wrap it up.